Have you ever stopped to think about what's really going on behind your screen? We're about to pull back the curtain on the secret engine that powers our entire digital world. It's like a massive, invisible team, all working together in perfect sync every single second. I mean, think about it. The final moments of a huge live sporting event. Millions of us, scattered all across the globe, watching the exact same thing at the exact same time. There's no buffering, no lag, it just works. How on earth is that even possible? It feels like magic, right? But what's actually happening is way more interesting. You see, the answer isn't some single giant supercomputer churning away somewhere. Nope, it's more like a distributed army, a legion of machines that take one massive problem and just shatter it into millions of tiny, easy-to-handle pieces. This isn't just teamwork, it's a symphony of computation on a scale that's kind of hard to even imagine. So, this whole idea of many hands make light work, it isn't just a quaint old saying. In modern computing, it is a fundamental core principle, and, you guessed it, it has a name. It's called parallel and distributed computing. It's basically the art of getting tons of processors, whether they're right next to each other in your phone or spread out across different continents, to all work together as one cohesive team. And the goal? Well, it's to do stuff that no single computer could ever dream of doing alone. We're talking unbelievable speed, massive scale, and almost perfect reliability. So why is this so critical? Well, it really boils down to four main things. First up, speed. I mean, we're talking about solving complex scientific problems in minutes that would take a single computer, like, centuries to figure out. Second is scale. This is how giants like Google and Netflix are able to process the absolutely mind-boggling amount of data we all create every single day. Third, efficiency. It's how a whole company can access the exact same files at the exact same time. And finally, you've got resilience. If one piece of the system breaks, another one just picks up the slack instantly. It's pretty much the reason the internet doesn't just, turn off. Okay, but not all of this computer teamwork looks the same. There are really two main flavors of it, and the difference is kind of like a small, elite special ops team versus a massive global army. And honestly, this analogy just nails it. Think of parallel computing as that team of chefs in a super high-end kitchen. Everyone's working shoulder to shoulder, communicating constantly, all focused on getting one incredibly complex dish out perfectly. It is all about raw, blistering speed. Distributed computing, on the other hand, is about building an empire, that global chain of restaurants. It's less concerned with how fast one kitchen is and more focused on making sure the entire worldwide chain runs smoothly, reliably, even if one restaurant, say, has a power outage. And, this isn't some brand new idea that just popped up. The dream of computers working together is pretty much as old as computers themselves. It's a story of evolution, really, that takes us from the research labs of the 1960s to the very fabric of our digital lives today. Just look at this timeline. The acceleration is incredible. We went from these clunky, specialized machines that filled entire rooms in the 60s to linking up regular office PCs in the 90s to suddenly having multiple brains or cores in every single computer we bought in the 2000s. And now? Well, now we're living in this world of ubiquitous computing, where the computer isn't just the box on your desk. It's a global network stretching from huge data centers all the way to the tiny devices in our pockets. So how do we make sense of all these different ways of working together? Well, there's a handy classification system, but let's just focus on the two big players you'll see today. You've got SIMD, which is like a specialist. It does one single instruction on multiple pieces of data all at once. This is what makes your graphics card so ridiculously powerful for gaming. It's doing the same thing to millions of pixels simultaneously. And then you have MIMD, the ultimate multitasker. It can do multiple things to multiple pieces of data. This is what powers everything from your smartphone to the world's biggest supercomputers. This all sounds amazing, right? Just keep adding more processors, and things get infinitely fast. But like with pretty much everything in life, there's a catch. There's a fundamental speed limit that we just can't get around. Before we hit that limit, let's define the prize we're all chasing. It's called speedup. It's a really simple idea. If one person can build a Lego castle in 10 hours, but 10 people can build it in just 1 hour, that's a 10x speedup. In computing, this is the holy grail. And here's where we hit that wall. It's a challenge that was brilliantly laid out by a computing pioneer named Amdahl. He had this incredible insight. No matter how big your problem is, some parts can be split up and worked on by the whole team,
But there are always other parts that stubbornly have to be done one step at a time, in order.
And this chart shows exactly why Amdahl's law is so important. Imagine you have a million-lane superhighway for 90% of your road trip. That's great. But if that entire highway has to merge into a single-lane dirt road for the last 10% of the trip, well, your overall speed is completely limited by that bottleneck. It doesn't matter how many more lanes you add to the highway, you're always going to be stuck waiting on that one slow lane.
But here comes the clever twist. Another brilliant mind, John Gustafson, looked at this and flipped the whole problem on its head. He basically said, wait a minute. When we get more processors, we don't just do the same old small problems faster. We use that power to tackle bigger, more ambitious problems. It's like going from building a little Lego car to building a life-size Lego spaceship. And when the project gets that much bigger, that small sequential part becomes a much smaller fraction of the total time. We're not necessarily finishing the same old race faster, but we're now competing in a much, much grander event.
So with all these laws and limits in mind, how do engineers actually do this stuff in the real world? How do you take a single huge problem and turn it into this well-oiled machine of parallel tasks? Well, it turns out there's a pretty standard 4-step playbook. It's called the PCAM model, and it's a brilliant little roadmap. First, you partition. You just smash the problem and its data into the tiniest possible pieces. Then, communicate. You figure out which of those tiny pieces need to share information with each other. After that, you agglomerate. You start grouping those tiny pieces back into larger, more manageable chunks to reduce all the chaotic chatter. And finally, you map. You assign those finished chunks to the processors that are free to do the work. It's this beautiful strategic dance of dividing, coordinating, and then deploying. And the truly amazing result of all of this mind-bending, behind-the-scenes complexity, you don't see any of it. It's a concept called transparency, and it's the magic that makes the digital world feel so simple and effortless. You don't know, and you don't care, that your simple search query just bounced between servers on 3 different continents. You don't even notice when a server in a data center halfway around the world goes down, because another one just instantly takes its place. The whole goal is to hide the chaos and just deliver a perfectly smooth experience to you. So we've gone from a single processor to what's essentially a global brain. And this journey has always been about more collaboration. And as we start pushing towards things like truly intelligent AI, immersive virtual worlds, and solving huge challenges like climate change, this teamwork is only going to get more and more important. The big question for the future isn't just about making our computers faster. It's about making them work together, smarter.